So today we're going to talk about section 7.6 in the book, plus a little bit of oops, oh, that's a really fat marker. Plus a little bit of how to work with the FPGA, basically, programming these module things, and we'll talk about what I mean by modules. Okay, but beforehand, let's talk about the hardware, right? So inside your FPGA, there's a thing called clock. Inside your computer, there's a clock. Inside everything, there's actually a clock, right? Inside you, there's a clock, right? You have your circadian rhythm. And previously, if you were to do this on a breadboard, we basically will give you this thing called 555 chip. So it's just, lucky name that that happened to be used for this particular chip when they patent it. And it's a 8-pin chip that basically gives you like a clock output at a regular time interval. Okay, so remember a clock, right? If you plot this as a function of time, it's just like high, low at some regular period, right? And therefore, it's telling you it's just a ticking of the clock itself. Okay, just imagine, the swing of a pendulum, click, tock, tick, tock, right? Pretty boring. Okay, so in order to utilize this chip, what you need to do is connect this chip. Let me just zoom out a little bit so I can have the pin out information also. You need 2 resistors and a capacitor, okay, outside the chip. Okay, so, and these 2 resistors and the capacitor is going to set basically the period of your clock, right? And also this thing called the duty cycle, and we're going to talk about what that is afterward. Even though the book doesn't cover it, so we'll talk about that. Okay, so the way this is connected is that you have some voltage supply. Let's just call this 5 volts, right? Whatever it is, right? Let's just make that 5 volts. Okay, and then you have a resistor connected to that. Okay, and we're going to call this point G. Okay, we're going to see why it's called G in a second. Okay, and then through another resistor. Okay, and we're going to call this point P. It makes makes less sense, and we'll see why. Okay, and then along this chain, right, you have a capacitor between you and the ground. Okay, right. This 5-volt power supply is also connected directly to pin number 4, right? And pin number 4 is the reset key. Okay, and we're going to see why that needs to be at 5 volts all the time. Okay, right. And once you build this little resistor chain, resistor capacitor chain, you're going to connect both point P to basically pin number 2, which is the trigger pin, and then pin number 6, which is the threshold pin. Where the heck is it? Is this one? Okay, right? Inconveniently on the different side of the chip. Okay, just to make it less convenient. Okay, and what's going to happen is that this output on pin 3 over here is going to give you this plus, on, off, on, off, on, off, on, off, okay? Where the period, okay, is going to be determined. It's going to be some function of R1, R2, and the capacitor, okay? And we're going to have an equation for that, okay? All right, but before we can figure that out, we kind of have to look inside the chip and see what's going on inside this little chip, okay? So inside the timer chip, okay, there's actually 2 op amps, okay? And what does this look like to you guys now that from last lesson? What is it called? Walk around on the beach. Yeah, it's the RS flip-flop, okay? Right? So inside here, right, is like 8 transistors, right? But we don't have to deal with that, or you can think about it in terms it's like, oh, it's like, 4 not NAND gates, right? Okay, whatever you want to think about. Okay, right. So inside here, okay. So unfortunately, this is also called VCC. So this is the voltage supply for the chip itself, right? Outside the chip, right, there's another voltage supply. It could be different, right, in general. But most of the time, you'll probably make this 5 volts also. Okay, just so make it easy. Okay, it doesn't have to be the same voltage power supply. Inside here, there is 3 resistors. Each of them are the same value, right? So if this is 5 volt here, right, this is going to be 1/3 of 5 volts, or 1.6, right? And this is going to be 3.3, right? So this is a 1/3, 1/3, 1/3 voltage divider, right? Because you have this voltage, you have this resistor, same resistor value down to ground, right? When you put them the same, they're going to divide the voltages evenly amongst them, right? Okay. Okay. And what you're connecting is that you're connecting this 1/3 one to the positive input of this op amp, okay? And then connecting the 2/3 to the negative end of this op amp, and you're going to see why that is important that we connect them on the opposite end. Because what we're going to do is we're actually going to compare, right, what we have. We're going to compare, right, these two, right? Because whenever, right, the negative is higher than the positive, this output is going to swing low, right? Whenever this positive input is bigger than the negative input here, it's going to swing high. Okay, they have an opposite functionality compared to each other. Okay, and these are, when you connect it this way, these are going to be called comparators. You're just comparing voltages on the two inputs. Okay, okay, because there's no feedback loop, right? So you're not amplifying it. Okay. Okay. Okay, so let's deal with this threshold and trigger connection, right? So the threshold, if we go back up to this diagram here, right, it's this IS thing, right? Right, it's pin number 6, and then the trigger is pin number 2. They are both connected to this point P. Okay, right? So, you know, there's a little pin comes out here, right? And then you basically connect them both to this voltage point P here. Why is that? Okay. Okay. So let's see what happens. Okay. So as when you connect this circuit up, what's going to happen is that, right, you have some resistors and you have some capacitors, right? Right. When you apply voltage to a capacitor, it does what? It charges. So the voltage difference between the two sides of the capacitor is going to increase, right? So if there was nothing here, right, there's no resistor, if this is connected to nothing, right, it will go from 0 to 5 volts at some characteristic time, right? Namely, right, the RC constant, the amount of time it takes for it to charge, right, it's going to be the R value of this times the capacitance value. And then since we have two resistors in series, this is going to be R1 plus R2, right? Because that's the effective resistance of two resistors in series, right? So this resistor is going to, this capacitor is going to charge up with some characteristic time, right? That characteristic time basically tells you when is it going to reach 1 over E amount of charge, right? Of the maximum charge, right? Right, 1 over E as in not the charge of electron, when as the exponential number, right? 2.817, whatever that number is, right? Okay. Okay. So what we can do is then, well, now that we kind of understand what's being connected here, right? The outside is this point P, and point P is increasing in voltage as a function of time, right? If you do nothing to it, right? Okay, it's going to charge up, okay? In fact, right, it's going to charge up as a function of time, and this is going to be plotted as a fraction of VCC. So, you know, you can just think of this one as 5, right? Just multiply all these numbers by 5, you'll get the actual voltage, right? Whatever fraction of VCC. The book likes to just keep VCC general, right? In case you have a 10 volt, 15 volt, you can do the same thing. Okay, so it's going to charge up. It's going to cross. Hey, David. It's going to cross these 2 points here. I'm going to describe what these 2 points are. But I'm going to blow past the first one first. Okay, it's going to go up and it's going to drop. It's going to stop charging. Okay, why does it stop charging? Okay, so I'm going to go. That's why we have to look at both these pictures at the same time. Okay, when this starts increasing, okay, it increases from 0 to. Let's use easier numbers, can we? Let's make this 9 volts, okay? Just so you have 1/3, right? So let's say this goes from 0, right? Right, when it reaches 3 volts, okay? Right, what's going to happen is that 3 volts, well, maybe 3.1 volts, right? just slightly over this 3-volt threshold here, what's going to happen is going to cause this comparator to output low, right? Okay. Or in other words, right, it's going to output 0 in digital language, right? So R is going to get set to 0. Okay. Right. But, right, this comparator up here, right, since we're at 3 volts, and this set these point to 3, this will be 6, right? 3 volts is still less than 6 volts, right? So this comparator over here also swings low, okay? We're just comparing two numbers, okay? 0, 0, okay? Okay? Okay. And remember that for an RS flip-flop, right? Right? You cannot change the output unless the output is one of the output, either S or R is set to high, right? In this case, if you want to change the output here, right, when you change R, you have to make sure that S is actually 1 first, okay? Okay, so nothing happens, right? When we cross this 3-volt point, let's just call this point 3 volts, this point 6 volts, right? And up here is 9 volts, just to make easy math, okay? Is that more confusing, or should I just say 1/3 the supply voltage? 1/3, 2/3. This is better with actual numbers? Okay. Right, just pretend it's a 9-volt supply voltage all the time, okay? Okay, so nothing happens because that flip-flop cannot change its output, okay? In fact, right, what's output here, right, is plotted down here in line down here, right? When it crosses that threshold, nothing happens to the output, okay? Not too interesting. But, right, when this output, this VP keeps charging up, right? When it reaches 6.1 volt, for example, right, this comparator is going to flip its output, right? It's going to flip this from 0 to 1, okay? Right? So at this point, let's say C, right? That's this point, right? At this point, right, what's going to happen is that I think I remember I said the wrong thing, right? You want S to be 0 if you want to change the output. If you want S to be 1, that variable is called set, right? Set means you cannot change the output, right? So when S is 0, you can actually change the output. When S is 1, you cannot change the output, okay? I think I said that the opposite last time, okay? Now that the comparator, this input R is going to be 1, right? It's going to get this input is going to get forwarded to the output, okay? Now output is 1, okay? And that's why when you get to 6.1 volt, or just slightly over 6 volt, that's when the output swings high, okay?
First comparator is connected to the set, right? So set is 1.
Oh yeah, set is 1. Sorry, you're right. Did I do that logic wrong? Yeah, they crossed this just to mess me up, right? And that means we actually want this comparator output to be 1 when it crosses, right? Does that make sense? Oh, you're right. Okay, my bad. Right, it's 0. Remember the RS flip-flop thing, right? The input R is always opposite of the output, right? Yeah, yeah. Sorry, I can just look at yesterday's, was it yesterday's notes? Did I do that? Or was that a couple of days ago? It's yesterday, right? When we did the RS, yeah, when we did the flip-flop, right? We want a regular flip-flop, right? Yeah, so whatever A is, right, X is always opposite of it, okay? Or the complement of it. Okay, good catch, Alan, sorry. Oops, let's go back. Go back. All right. So whatever R is, output is going to be opposite of it. That's why it swings high when you change your set from 0 to 1. Okay? So what I said initially was correct. Okay, double corrected myself.
Set as 1, then you can
Change the output, yeah. Yeah, it's ready to be set. Okay. All right. Okay, so what's happening here, right? When you set this output to 1, it also, okay, basically this output is also connected to this little transistor inside here that's connected to the discharge channel. Okay, this discharge channel, if you go back up to here, is actually pin 7. Pin 7 is connected to whatever this G point is. G meaning, I think they try to mean ground. Okay, because what's going to happen is that, right, by making this output equal to 1, the base of this transistor, right, is now at, 9 volt, whatever it is, right? It's going to turn on this transistor. When you turn on the transistor, whatever charge is here will get drained out to ground. Okay? Basically, what's happening is that now that that ground point, right, that was up here, right, whatever voltage that's here is going to start decreasing. Okay? It's going to try to go towards ground, okay, at some characteristic rate. We're going to see what that is, right, by draining current through this transistor, and that's why the voltage at P is going to start dropping, okay, okay, but it's going to stop, right, when the voltage at P goes below, it's just slightly below whatever this, just slightly below 3 volts, and therefore it flips this comparator, right, back from 0 back up to 1, right? And then the output changes from 1 to 0, right? It flips, okay? And now, right, this discharge gets turned off, okay? Okay? When this turns off, it stops the discharging, and it's going to start recharging and discharge, recharge, discharge, recharge. And you may say, well, that's not a clock, right? Right, that's just a seesaw. It's actually a weird seesaw thing. But on the output, what's happening is that this output is going to go from 0 to 9 volts, up and down, up and down, up and down, as the seesawing is happening. Okay? And that's exactly what you want is a clock. Okay? Okay? Circuit makes sense? Right? You're just charging, discharging a capacitor at regular intervals so that you can actually see the output. Okay? All right. So there is a characteristic time of this, right? So there's some, you want to figure out what the period of this, or maybe the frequency, right? Which is just 1 over the frequency, 1 over the period, okay? And there's a little derivation that the book does, which is, fine. We can just go through it, right? And remember for the voltage on the capacitor, right? It basically kind of is proportional to some exponential growth, right? So when you charge a capacitor, it charges exponentially. When you discharge a capacitor, it decays exponentially, right? So whatever the voltage at point P is, right, it's going to be proportional. It doesn't, we're just doing proportionality at this point, okay, to some time divided by some characteristic time known as the RC constant, right? And this tau, right, when you're charging, right, it's going to be R1 plus R2 times C for charging. Why? If we go back up to here, oops, you have to go outside the comparator, sorry, the timer, right? When you're charging from this source, right? And you have to go through 2 resistors to charge it, okay? When you discharge, okay, when you discharge, right, you're discharging the capacitor's charge through only 1 resistor to ground, right? You only have to go through 1 resistor. So there's actually 2 different characteristic time. You can actually kind of tell, right? Because this exponential growth and this exponential decay actually has a slightly different slope to it. Okay? Okay? So the discharge time constant is just R2 times C. Okay? Okay? In fact, right, we don't actually want to fully charge or discharge the capacitor, right? We're oscillating between the 1/3 full charge to 2/3 full charge all the time, up and down all the time, right? So the ratio of this to go from 1/3 to 2/3, right, is going to be, you know, 1/3 divided by 2/3, right? And so basically the 1/3 just cancels out. You have 1/2 on this side, right? And if you solve this equation for t, you're going to find out that, well, the amount of time for it to charge is just going to be natural log of 2 because you natural log both sides, right? Times whatever the characteristic time is for both of these together, okay? Right? Since this is an exponential function in here, when you multiply both of those together, right, you're basically just adding, right, when you have e to the minus t tc, right, and then you multiply by e to the minus t over t tau d. I'm trying to write taus instead of t's. Tau d, right? That's the same thing as e to the minus t tau c plus tau d, right? Because this is an exponential. Okay. So what's happening is that, well, when you add these two numbers together, right, r1 times c plus r2 times c plus r2 times c, right? That's r1 times c plus 2 times r2 times c. In other words, it's the same thing as r1 plus r2 plus twice r2 times c. Okay, and this number of 0.693 is just natural log of 2, right? Just because you're charging it to 1/3 and then 2/3 of its full voltage. Okay, right? And you can calculate this, right, by just plugging in R1, R2 capacitor value, and then you will have the period of this clock, up and down, up and down. Okay, if you want the frequency, you take 1 over that, right? Okay, right. That's how you set the period on a physical clock chip if you wanted to do that. And yeah, and in the past we have done that, and that was like, you know, part B of some lab or something like that. But now, since we have these basis board, we just have a clock, so we don't need to do this chip anymore. But it's just good to know in case you do run into this in the future, how to deal with these chips. Okay. Right. And something else that's not covered in the textbook, unfortunately, I don't know why, is this thing called the duty cycle. Okay. The duty cycle basically quantifies, let me go up here, what fraction of the time, right, the clock is high versus the total amount of time. That makes sense, right? Because you can actually maybe, like, instead of having a clock that's very, you know, narrow like this, you can have very fat clocks, right, where it's up most of the time or down most of the time. And the reason you want to do this, maybe you want to actually use this clock to power something. So you want the duty, so the amount of power going out to be higher. And we're going to see this in a couple of labs when we do this thing called pulse width modulation, where this width is actually going to determine how much power is being sent to a speaker. Okay. Okay. And this is sort of interesting because in this little chip, you can also set the duty cycle, because the duty cycle is basically the amount of time that the clock spend being on high mode divided by the total number of time, which is the amount of time is on high mode plus the amount of time is on low mode, right? Right, at 0. Okay. Well, we have an equation for when the clock is high, right? That's just the 2 resistor times the capacitor value, right? And then when it's on low, right? This is the single R2 resistor without R1 times the capacitance value. Okay. So you just plug this into this equation. What will going to happen is that, let's say if we make both R1 and R2 a 1 kilo ohm resistor, okay, right? You multiply this out, the capacitor value actually cancels out. So the capacitor value doesn't actually change the duty cycle, but it does change the period, right? Okay, multiply this out. There should be, yeah, this is added, so you can actually cross both of them. You compute this, the duty cycle is actually 67% if you make the resistor the same. Okay, usually you actually want the clock to be half the time up, half the time down, right? So In order to do that with this 555 timer chip, or in just a lot of these chips in general, what they do is they put a very large resistor for R2, a small resistor for R1. Okay, you can, in this example here, right, if we put a 10K at R2 and keep the R1 at 1K, you get close to about 50%. In reality, you never actually get to exactly 50%. Okay, right? So that's how you can change the amount of time your clock spends being high versus being low. Okay, but that's why you have two resistor to tweak. Okay, right? To get the period, right, of the clock, right, then it's both of them combined together, right? It's this complicated formula because you have two resistors in there. Okay. All right. Let me just go through an application of this before we go into the FPGA stuff. Okay. So one application of this is known as a switch debouncer. The book also talks about this. So a lot of times when you push a button, right, what's going to happen is that when you push that button, right, so there's a physical, let's say you have an actual button, right, you're making contact between two pieces of metal, right, and the button, right, usually what you want is you want like maybe 5 volts here, and this is usually connected to ground through some resistor, right, and initially there's no charge on here. This is 0 volt. When these two objects get close to each other, electrons start getting shot between them because now your electric field is getting bigger and bigger because the distance between them gets smaller and smaller. Okay. So what's happening is that you're going to have a situation where the charge is going to start bouncing up and down here. So instead of, when you push a button, instead of a nice pulse where, oh, let's say the voltage here, right? Voltage is C. Yeah, let's call that B. Voltage at the button, right? Instead of the voltage being at the button just going straight up and then staying high, what you actually see in reality is that it's going to start oscillating up and down and up and down, up and down like this. So it just creates a lot of noise, and then it goes high, okay, when you have a solid connection between them, right? Okay, this is called bouncing, right, because it's bouncing up and down, right? But what you can do, right, is use a RS flip-flop to make a debouncer, okay? And I think in one of the labs we actually make one, okay? Right? So let's say instead of this little button thing, you're trying to switch the power from one to another, right? So both of these are at 5 volts, and then you're using this to power some light bulb. Just imagine this is a light bulb or something like that, right? Just power going through it. So you want to switch from this power supply to this power supply, okay? What you want to do is flip the switch over, right? But while you're flipping that switch, right, both lights are off, right? So now you're in the dark momentarily until you get to the other side, right? So this is another application of debouncer where you can keep a device on without losing power. Basically, imagine this as like an uninterruptible power supply. Anyone heard of that before? No, people don't use that anymore. UPS, yeah, yeah, okay, yeah. And this is basically the function of these UPS to switch you from one power to another without turning off your device. Okay, okay. The way you would do this, right, is you connect this to an RS flip-flop. Okay, right. So you have 5 volts here. So remember that when at the current state, this is on high, right? So now you have current coming out here, right? This is set to 0. S is set to 0. The set function in our RS flip-flop is set to 0. And now we remember, right, that when S is 0, you cannot change the output, right? Okay. But when this gets flipped over here, okay, right, this thing, the R on this side basically goes to 0 right away, right, when you disconnect it, right? So, but the output stays high because S is still at 0, right? So, but then once that's it, your switch connect to the other side of the circuit, right? Now S goes to 1, okay? Okay? And now, right, since this is going to 1, right, this is at 0, um, on this side, right, since this S is going to be opposite of this, it's going to go to 0, and it's going to force your output to stay at 1. that make sense? Right? Because remember, this is Q, this is Q bar, right? It's always opposite each other. Okay. Okay. In the FPGA, in the FPGA lab, I think one of these, yeah, you have to make this little circuit here, where you're gonna be debouncing one of these buttons. Unfortunately, I have a picture of it. So on your FPGA, there's these little buttons, right? Those little buttons, right, is basically what I drew up here, right? Where you push a button and you make a connection, right? And it's gonna do this bouncing thing unless you debounce it, right? Basically by buffering, that's another word for debouncing, by buffering the output so that you don't have this oscillation, this bouncing function, okay? And this is going to bring us up to this idea of a clock, okay? Where we're going to use the clock as a way to buffer this so that however you're pushing the button, this bounce action is never going to be faster than the clock, okay? Okay. All right. Let's not go through this little circuit diagram. Because it's gonna take like 15 minutes to do it. But what I want to show you guys now, right? So we have a little bit more time. What time is it? Okay, it's already halfway through the lecture. To show you guys a little bit about the Verilog code and how, because I think today you guys are gonna start programming in Verilog, right? In Vivado, the little software program. Just want to show you guys a couple of things that might help you smooth things over. Okay, right? Last time I showed you guys how to make a top file, right? I think it's lowercase f actually, right? The first time I showed you guys how to do it, I basically told you to use one input, one output. The first input is switch, the output is LED, right? And these are bus outputs, input outputs, right? So you have 16 bits on each, right? 0 to 15 counts up to 16. Okay. If you want to add the clock, right, into your code, you want to utilize the clock, right? That's actually called CLK. So unfortunately, the font is kind of small. You can see this, right? And the clock is an input to your code, right? Because, right, the basis board is actually making this clock all the time by itself. You don't have to set it up. But unfortunately, it's a 100 megahertz clock. So it's a very fast clock, okay? I mean, you want a very fast clock on your computer because, right, then it can do a lot of things. But, right, we're not going to be able to see things at 100 megahertz, right? You can probably see it on an oscilloscope, okay? So there's two ways to do this. If you want to add the clock to your Verilog code, you can either make a new top file, right? And then just when you make a new top file, it does this thing where it asks you, oh, what's the module definition? And you put your switch, you put your LED, just add your clock to it, okay? Okay. And since clock is a single thing, it's not a bus, right? Okay. So don't bust your clock. Okay. The other way you can do this is just like physically type that in yourself, right? So initially, when we did it last time, it only had this, right? What you can do is just put the comma and then just add a line for the input clock. Okay? Okay. And that'll allow you to grab the clock from your FPGA. Okay? Right? However, to use the clock is a little bit different from your wires and your LED and your switch that you use so far. Because the clock is a continuous thing that's going up and down all the time, right? So things are happening in sequence when you're dealing with the clock, right? One clock follows another, right? The other stuff I've shown you so far with the switches, right? Once the switch is, switched to one, it stays there, right? It doesn't change, right, over time, right? It's you flipping that switch that changes it, right? Okay? So the stuff we've been doing with the full adder, well, you're going to do today in the full adder, this is known as combinatoric logic, okay? In order to deal with the clock, you're going to have to think about this thing in terms of what's known as sequential logic, okay? Okay. In this class, we're not trying to go too much into theory of the difference between the two. right? But the practical application of that is that when you do want to use the clock, okay, instead of just saying, oh, I want to, you know, you cannot just say, switch. Let's say, you cannot just say LED 0 equals to clock. Okay, that's not going to be a valid statement because, right, the clock is changing all the time, and basically what's happening is that you're connecting and disconnecting a wire on your FPGA all the time if you did that. Okay, right? In order for this to happen, what you need to encode in, so this is actually the code itself, but you're going to have this always at, okay? Always at what? I don't know, right? At the POS edge of the clock, and then begin something. Okay, when you begin something, you always have to end something, okay? Right? So what this stands for is that always at the positive edge of a clock. Why does it say positive edge? What's the opposite of positive edge? Negative edge, right? So when the clock comes in, right, it's going to be timed so that this little block of code gets executed all the time at these positive edges, okay? You can also have it execute on the negative edges, hence utilizing your DDR memory, right? Right? Okay. So this gets executed over and over and over and over again every time the clock goes from low to high. Okay? Right? And we're not going to talk too much about this for now. But I just wanted to make sure that you don't get stuck on this when you're writing your code to do this, okay? So yeah, as I mentioned, you cannot just assign, a LED to be that, to be the clock. Let's just say that, right? Because what's going to happen is that this is going to happen like 100 million times per second, right? Okay, and what you're going to get is you're going to get this thing called procedural assignment not allowed or something like that. It's some cryptic language, right? It doesn't say, oh, you're mixing up your sequential logic with your combinatorial logic or something like that, right? That'll be helpful, right? But this is not. Okay, so what you need to do, okay, and unfortunately I kind of have to talk a little bit ahead of what we're going to talk about next week. Okay, we're going to have to, instead of directly assigning the state using the clock state, we're going to have to use this thing called a registry. Okay, registry is just a fancy name for memory. It's just a a little piece of memory. Okay, what you want to do, instead of changing the LED directly, you want to change the registry instead. Okay, yeah. Okay, and the way you change a registry is also different than assign. You cannot just assign something to be a registry. Okay, so let's just go through this little piece of code so that when you guys run into the clock, you're not going to be just like, why am I doing this again? Right? Okay, to make something a registry, you have to type reg in front of it. Okay, hopefully that makes sense. I'm just going to call this my clock. Okay, I'm just going to like copy the clock over. Okay, this is kind of boring, but so you have the clock already, right? And this clock in the basis board is going up and down at 100 megahertz. Okay, 100 million times per second. Okay, so what I'm going to tell it to do is I'm going to tell it always, whenever the clock goes from low to high, okay, do something. Okay, what I want it to do is I'm going to set my clock to be the opposite of my clock. Ugh. Okay, right? This symbol, okay, is the registry assignment. Okay, you're basically, think of this as kind of like a pipe. You're piping whatever's on the right hand side into the left hand side. You're shoving whatever's on the right into the left. Okay, right? And you have this arrow to tell you which direction we're shoving things. Okay, right? Okay, so right, this may be confusing. It's like, wait, why would this make any sense, right? Let's say my clock, right? I didn't even set this number, right? Originally was initialized to be 0. Okay, okay. So when the positive edge comes, right, my clock gets set to be opposite of my clock, right? It goes from 0 to what? To 1, right? So this changed to 1. Okay, but then next clock cycle comes, this is going to keep happening 100 million times per second. when the next clock cycle come, right, my clock is no longer 0, right? My clock is now 1, right? While opposite of 1 is 0, right? Okay? And so this keeps happening, 0, 1, 0, 1. If I can write 0, 1, that would be nice, right? And then a similar thing. So basically, I just copy the clock. Okay, this is kind of boring. It's not very useful. You probably don't need to do this ever, right? And now, right, since my clock is a registry, it's a wire that is connected. It's a piece of memory bank that is inside my FPGA. It's a flip-flop inside my FPGA, right? What I'm going to do is I'm going to physically connect a wire between that flip-flop to my LED. Okay, now I can get that LED to blink up and down, up and down, up and down 100 million times per second. Okay, so I cannot assign the regular clock directly to my LED, but I can make a registry, which is a little piece of flip-flop inside my FPGA, right, and connect it directly to my LED. And whatever state that that flip-flop is, my LED is going to replicate it. Okay. Does this make any sense, especially for the non-CS people?
Makes sense, but I don't understand why we would want to do that if we have.
This code is useless. All right. Yeah, this code is useless. But you are in order to deal with clocks, which happens over and over and over again, you have to go through a registry because you cannot assign. The registry is kind of like, you know, the little storage buffer, so that because if you try to assign, you know, LED directly to your clock, what's going to happen is that it thinks that, you know, every cycle you want to change the wiring inside your FPGA. Because remember, when you program your FPGA, what you're doing is you're basically, right? Remember what the FPGA physically is when we started talking about this, right? Physically, the FPGA is a bunch of wires that's crossed on top of each other. When you program the FPGAs, you're just connecting that cross or not, right? So you don't want that cross to connect and disconnect all the time, right? You want to hardwire the flip-flop to your LED, but your clock keeps going up and down because you can't, right? So you cannot directly connect it to it, okay? Hopefully that makes sense, sorry. Okay? It makes sense after you deal with hardware for like, you know, a few years. Okay? All right. Okay. Shit. Sorry. Okay, still got 10 minutes. That's not too bad. Okay? Everybody happy about that? Okay? Why you have to go through registry whenever you're doing something that's changing each cycle of the code. Okay? Basically whenever you're using the clock, you're gonna have to deal with registries. Okay? And we're gonna talk about registry next lecture also. Okay? Okay. The other thing you're gonna do this lab that you're gonna hopefully finish today is you're gonna build a 8-bit by 8-bit adder, right? In order to do this, right, the lab kind of takes you through how to build your first adder, right? You built one this is one your full. This is your first full adder will look like this. Okay, we don't have to go through it because you're gonna see it. I cross out the part where I'm trying to get you to actually write the code yourself. Okay, so you can't see it. And then it's gonna tell you to make your second adder by just, you know, you take a copy of this, right? You paste it down here. You change all the ones into twos. Okay, right? That works if you want to do 2, but if you want to build a 64-bit adder, that'll be kind of annoying, right? So what you can do instead is you can make this full adder functionality into something called a module. Okay, where have we seen a module already? Which module have you dealt with already? The top module, right? The top module, right? This is a module already, right? So module, end module, right? So they start and they end, right? That tells the FPGA when your module is. Okay. The top module is the one that gets executed first. Okay. It's basically the boss module, and what the boss module can do is like call on other little modules to work for it. Okay. Okay. So those of you who already does programming, right? These are just functions, right? Or what is it? Classes. You know, they're all this different names for very similar things, right? Okay. So you can make modules instead. And so in Verilog, they're called modules, or in other languages, they're called different things. But what you can do is that you can declare these modules after, so this is this is the end of the top file module, okay? You have to declare after your top file module, okay? And I think the lab actually gave you this, so I don't feel bad, giving this to you guys, right? Where you have to declare another module, you can call it something, and hopefully if the functionality of this module is a full adder, you would call it a full adder. Okay, don't call it, Bob or something like that. Okay, and then what's important on these full modules is that they're going to have inputs and they're going to have outputs. Okay, the way, especially those of you guys who are not programmers, and this is not a programming class, you should think about these little modules as little machines, or like appliances in your kitchen, or a factory that does certain things, right? Okay, the way you want to think about it is that if you give it some input, it does some functionality inside it. Okay, you don't need to know what's going on inside, and it gives you an output. Okay, I think the example I gave last year is that if you give a blender, the blender is the module, right? If you give the blender, strawberry, banana, and yogurt, right? Those are the three inputs. It gives you, smoothie as the output, right? Right. So that's how you want to think about this physically. Okay. So in declaring these, in defining these modules, you have to give it the inputs. I'm going to call the first input A, the second input B, the third input Cin. Hopefully that sounds familiar, right? And the first one of the output is going to call L, the other output is going to call C out. Okay, carry out. Okay, and then inside here is going to do some machinery, right? That you're going to have to encode yourself. Okay, I think I gave you the first line. The second line you have to write yourself, and it's going to change what L and C out is, right? So basically, this is your banana, your strawberry, your yogurt, and this is like your smoothie. I don't know what's another output of a blender. I don't know. Maybe like, cold. Make it cold. Okay. Maybe that the smoothie is not a good example, okay? Because you only get one output, right? Okay. Juice, maybe, yeah. Okay. Anyway, so that's how you want to define these things, okay? So you can define these modules after your top file module, okay? Whatever that is, right? Okay, you can see the line number is 87, right? Okay. So you can also not only define these, but you can also import it using this add design source function. Okay, we went through that a little bit. So let's just look at what this looks like. Okay, so remember when you add a source file, right? You can add either a constraint file, a design file, or a simulation file, right? A design file is basically what all these modules are going to be. Okay, so instead of adding, right? Instead of creating a new file, you can just add the file itself. In fact, the lab is going to tell you to, because we're going to use this function, this little module called hex display v2. We're going to add this into our code without even you can look inside this file and see how it works and stuff like that. You don't even need to look inside it, right? Because it's basically a machine that now you have to make smoothies and juice for you, right? Okay, right? So when you add these things, what you need to do, right, in your top file, you have to do this thing called instantiation, okay? This, maybe I think some CS does the same thing, use the same language for that. You basically, when you instantiate a module, you're basically taking that, juicer or blender, sorry, blender, right? You have to make a copy of it, okay? So technically, you're actually never taking the blender out of your cupboard, right? Every time you instantiate it, you you make a copy of your blender, and you put it on your kitchen table and you use it, and then after you use it, you delete it and it goes away. Okay. All right. So to instantiate a module, what you need to do is know how to instantiate it. Okay. So this is a instant of this module. Okay. And this hex display thing is a complicated module. So it needs a clock, right? Because it's going to change what's going to be displayed on these little decimal numbers. It's going to change, okay? So it has to do things multiple times in your program, right? So whenever you have to do things multiple times, you're going to need a clock, okay? And this L is basically the 16-bit binary values of the numbers you want to display, okay, instead of, ones and zeros. So this L is going to be some chain. Actually, this is going to be we're going to make this a wire L. I think we need to do this beforehand. 15 dot 0 L. Okay, that will allow you to make this long L. We're also going to use this thing called button C. Button C is the center button on your FPGA. There's a little 5 buttons on there. So in order to use this button functionality, we have to add that as an input. So you can either type that in, or you can make a new top file and then add that. Okay, but I think typing it in is pretty easy. Okay. Okay. One quote B1. Those of you in CS might know what this means. Any guess? Yeah, B stands for binary. It's a 1-bit binary with a value 1. Yeah, basically you just gave it a number 1. Okay, all right. And then seg, it stands for the segments on your FPGA. So it's basically the way it figures out how to display the numbers is to figure out, right, on the digital display, right? There's, in order to display all the different possible numbers, right? There are 1, 2, 3, 4, 5, 6, 7 segments. Okay, and this segment is 7 places long. Okay, it just basically tells the display which part of the segment to turn on, right? So if you want to display 7, you turn on this segment, this segment, right? That'll display 7. Okay. Okay, and okay, it specify, since this is a 4 decimal place display, it also tells which of the 4 you want to turn on. Okay, so that's why this has 4 bits. Okay. Okay. So to make these modules, you can either add it to the end of your top file, right, like this, or you can import it. Well, import by meaning just add the file, and then once you have that file inside your project, right, now you can use these functionalities. Okay, but you have to know how to use it by instantiating it. Okay, okay, because this is inside your top file, right? Okay. Oh, one thing I want to make sure. Okay, to instantiate things, right, the first thing you need to do is tell it what you want to which blender do you want. Okay, the blender we happen to want for this hex display is called hex display v2. Okay, version 2. Okay, and you have to call it something locally. Okay, so instead of calling it blender, I'm going to call this blender 0, blender 1, blender 3, because I'm making clones of it basically. Okay, and then you do these arguments to give it the input and output it wants. Okay. All right. So you're gonna see this in towards the end of lab 9 today. Okay. All right. I think that's all I got.